Hi everyone, in this tutorial we will be looking into the introduction to multi-GPU programming. So the aim of this tutorial is to get a better grasp and better understanding of the basics, primarily the basics of communication and synchronization, which are the most important things that are happening in a distributed in a parallel computing environment. If you want to go a bit deeper and more on the computer engineering kind of side of things, you can look into the things that I describe here. These keywords that you can use as starting points and Google to better understand some of these theoretical concepts that are crucial in distributed computing. For this tutorial, we will first look at very simple basics exercises, just for understanding how the simplistic operations work, and then we will have a bit more complicated example where we do one layer classifier, see how it would be done using the basic functions, and then we see how easy it is to just scale up to multiple GPUs using PyTorch Lightning. So some first initial considerations regarding running the code. We will have access to the Lisa GPU cluster, but it is not necessary to run this. It's nice to be able to play around, but everything is included in the tutorial, also the results. So this is not a requirement. What you can do if you want to look into this is that you can SSH to log in into the Lisa cluster, then use the module package system to load the Anaconda system, and then create an Anaconda environment using the environment.yaml file that has been provided. Here I also describe how we can upload files using Rsync. This assumes that we have some Unix-like system, so like WSL on Windows or Ubuntu or any other distribution or macOS. Once we are in and we have loaded, we're capable of creating the environment, we can now run an interactive job. Interactive jobs allow us to get into the machines, have access to the multiple GPUs, and then play around inside of it. And here I set aside 1 hour of time for this interactive job, but this then depends how long you want to stay there, how many credits you have, and these considerations. Once you are inside, you can just run the script and you will see the results. The images will be created when there are images, or you will see the printouts in screen. So the first thing is that here I describe some useful utilities that we will be using during the tutorial. So this is, for example, a nice print that gives us also the rank of the GPU that it's currently printing this message. This makes sure that we don't have ambiguity on which GPU is saying what. Then we have a disk function. This disk function simply draws a disk inside a matrix. The square draws a square inside a matrix. And then the plot matrix simply plots out this matrix. Call it matrix. Technically, it's an image, or with one single channel, see it as you like. We have several different backends to do distributed computing. They're available from PyTorch. These are the Glue, Nickel, and MPI environments. We will be using the Nickel backend as it is the one that works best, that has the most functionalities in the NVIDIA GPU setting. But also other things are available, and you can look into what is best for you depending on the current configuration that you're running. We need to remember that on Lisa there is a Scratch folder where you can quickly access, because the Scratch folder is always located in the same, or at least close enough to the node that you are currently running on. And so we will use that as the primary file location when we need to quickly load and write stuff. And we have the main function that actually starts up a distributed environment setting. This is really, really simple using the PyTorch distributed library. Here we simply set the device, which currently will be, for example, device 0 or 1, depending whether or not we are in GPU 0 or 1. And then we will initialize the processing. This will define the backend, which will be nickel in our case, and the world size, which in our case will always be 2. We will be using only 2 GPUs. And then the initialization method, which in this case we will be using a file. When we have multiple nodes, we can also use TCP, or we can see what is the best then method of communication between the different nodes in our group. And then the current rank, it's not necessary to give the rank the same ID as the GPU, it's just convenient in our case. And then we just return the device just because we can use it for other processing later. We will see. So it is, I think, important to keep in mind that the overall goal it would be then to do some training of these models, of our deep learning models when you have multiple GPUs. So we have seen the broadcast operation. This is clearly something that we can use to spread around the weights of our model. Then we've seen the reduction type of operations. That is clearly the best candidate, the one that we will be using when we want to compute the final loss. We start with a batch size. Let's say this doesn't fit in one single GPU. We spread it around multiple GPUs. But then we need to compute the loss. We need to average over the entire batch size. And so we can use the reduction. And the operation that we can do with the reduction varies depending on what we're trying to do. We can do the sum, the average, the product, the min, and the max. Average only with a certain version of nickel. So for now, we stick to the most simple ones. And you can test them out if you're running the scripts on your own. You can try out the different operations, see what changes. It's pretty straightforward. So now we can start with the analysis of what the actual operations that we can perform, the type of communication basically that we can establish between GPUs. The first one is the all reduce operation. This one takes some tensors, some information, some data, and then it sums it over all of the GPUs, and it also spreads it around each GPU, the results, so that now all the GPUs will have the same results. This is why it's all reduced. So in our example, what we will do is that once the script starts, we will spawn 2 processes. We need to have one single process for each device. This way we don't encounter problems with the fact that Python does not really allow for multi-threading and these kinds of problems. So we just spawn a new process for every device. Here we just have 2 devices, so 2 processes. And then each of them will just take a hold of one GPU. And in that GPU, depending on whether or not it's the rank 0 and rank 1, it will generate a different image. Here, the one with the circle, and here the one with the square. And then we perform the operation, the all reduce operation with the max, which results in this final result here. So we can see how both GPUs have now access to this information. We can now see the reduce operation, and this is pretty much identical up to the reduce, which now has a specific destination in addition to the operation that we want to perform. Because still it takes all of the tensors from all of the GPUs, but now it only sends it to one single rank. And PyTorch allows to define the destination, even though in the nickel documentation we see that it sends it to the root rank. Here instead we can decide which one to send it to. And we can see here that if we take these 2, we still perform the max. The rank 1 GPU now still has the same input as before, while now the tensor in the rank 0 GPU, which is the one that we decided as destination, will be updated. Another fundamental operation is the broadcast. We start from having the tensor in one single GPU, and we can then broadcast this. We can send it to all of the GPUs in the group. So here we can, in PyTorch, define which is the source rank instead of just having the root rank. And we can see here, this will be the result that you will see. It will save these images for you. And you will see that the rank 1 didn't have anything, it just had something else. But now it will have exactly the same the same matrix, the same tensor that was in the rank 0 GPU. We now go to the all gather operation. This is also quite straightforward in the sense that we simply take a subset of the information and we send it to all of the other GPUs. So that now that all GPUs will have all of the information that was initially only present partially in each GPU. So here it's really, really important to understand that it's not a problem of memory anymore. We usually talk about multi-GPU as well, we don't have enough memory in one single GPU for our batch size. But here instead, it's more a type of operation to improve the speed of computation. We have something that has been performed in different parts of your input. And so you can spread the input around, do the operation in 1/4 of the time if you have 4 GPUs, and then distribute this final information again to all of the GPUs so that processing can continue. And so we can see here, in this simple example, this image and this image was only available in rank 0 and rank 1 respectively, and now it's available to both of them. The reduce scatter is also another example of an operation that is useful when we want to speed up performance instead of having problems of memory. And so here we do a reduction operation. So again, it can be max, sum, product, min, etc. But now we only send the partial result to each rank. So this is simple to see with the example. We have some information here and some information in the other rank, and then we perform the maximum. And we can see that only the rank 0 has the result of this maximum on the top ones, and only the rank 1 has the result of the maximum of the bottom ones. And so this was really, really simple operations that we can use to build up then something more complex. As an exercise, you can look into actually what is the best combination of number of like the batch size effectively, or what is the number of tensors that you can put in one single GPU. Is there a sweet spot that is maybe given by the multiple of the tensors, or does it not matter? Is the performance negligible? You can look into this. It is a quite interesting topic, and it's important to keep in mind when we work with more low-level type of operations. Much less important, much less crucial when instead we're using big libraries that have already made all of this processing quite efficient for us. We can now look at a more comprehensive example. So we take an input image, we flatten it out, multiply by a weight matrix, compute a softmax, which allows to have predicted class belonging probabilities. Then we compare them to the target with a loss, cross-entropy loss, and we find out how well our model is performing. And then we could keep going and compute gradients, etc. But for now, this is all we're doing. Very simple, straightforward, but these are basically the core types of operations that we would be performing on a real model. So the first thing that we need to know is that we will be doing a broadcasting of the weight matrix from one single GPU to all the other ones. This is quite slow. It's much more efficient if all GPUs already had all of the weights and they keep their own local copy updated at each iteration. This is also an example of how slow data parallel is, and instead what is better, what has been improved in distributed data parallel for PyTorch at least. And then we have the reduction operation. So we take this blue and this red results, and then we do the sum, we reduce them, and we do a reduction that spreads them in all ranks, so that now we have available our loss. So the structure is still pretty straightforward actually. We spawn the two processes in the beginning, and then we set up the environment, and then we load the dataset. This is the first time that we will see a use for the barrier operation, let's say. So a barrier allows for us to ask the process to wait until all of the processes have reached this point in the execution of the code. In this example, it's really crucial because we're only letting rank 0 download the data. Otherwise, we would have a bunch of different processes that are trying to download the same data inside the same place, and it's not very nice. And then the other processes will not have the data yet. They will just skip this if statement, and they would start doing the rest, but they don't have the data yet. So they need to wait until rank 0 has finished, and then we can actually do the loading of the dataset, the initialization of the dataset correctly. And all the other processes will now find that the dataset is present in that folder. Then we have some simple definitions of the input size, the batch size that we want on each GPU, and the number of classes. Here it's CFAR 10, so it's 10 classes. Then we initialize the weight matrix, and we initialize this only on the 0 rank. And then we ask for a broadcasting. Now, this broadcasting operation has been done asynchronously. So an asynchronous operation allows for us to start this operation, and then the execution of this code can still keep going. We don't need to wait for this I/O operation to be performed. So the other GPUs will now be waiting to receive the rest of the data before they can keep going, obviously. But GPU 0 can keep going. So they will take the input and the target, we just define them, and then we load the images one by one. So this is a loading from disk directly then to GPU, which is one of the most time-consuming things that we're doing when we do training of neural networks. We then perform the multiplication between the input and the weights. We do log softmax. This prepares us really nicely to then compute the cross-entropy loss with just a sum operation and a mean. But now this is not done. This is just a partial loss on those 128 samples that we had, not the entirety 256 that we would like. And so we do a reduction that goes to the rank 0 with a sum operation. Then we divide by the world size to get the actual average, and we will have the final loss at the end. So we see here that there is quite a lot of few elements to keep into account, to look after in order to have multi-GPU training be successful. But in the end, what we can do with PyTorch Lightning is extremely simple. In the trainer, we just define the number of GPUs. We could also define the number of nodes. We can select the simple strategy of distributed data parallel. And then the multi-GPU training will just start. So in this tutorial, we've seen how the primitives of communication in a distributed environment work. So we have looked into the all reduce, the reduce operation, the broadcast, the all gather, and the reduce scatter. We've then seen a more complex example of how these things can be put one after the other together. Also, we've seen an example of the barrier and asynchronous operations, how they can be useful. And then we have seen how easy it is to perform these operations in PyTorch Lite.